Running through again the basics of this hydrostatic balance, we basically looked at the pressure at the top and the bottom. We looked at the mass of the air in the cylinder, and we did a simple mass balance by looking at the gravitational pull, pressure from the top, pressure from the bottom, and we came up with this hydrostatic balance. Okay. This has many applications and implications in ocean and atmosphere science, as we'll see along the way. And one of the cute things is that given the pressure at any level z, you can simply integrate from that height to infinity, because the atmosphere disappears at some point to zero pressure. And what do you get when you integrate density times the height of the column over that height, right? Multiplied by g. That's your mass, right? So what does it say? Pressure at any height is equal to the mass of the atmosphere above. Very nice, right? So that's how we kind of can estimate the mass of the atmosphere. If you take surface pressure, easy enough to measure everywhere on Earth, that's got to be equal to gravity times mass of the atmosphere divided by the surface area of the Earth. So this is how it's easy enough to estimate the surface area of the Earth. We know the gravitational constant, so this is how we estimate the mass of the atmosphere as a consequence of hydrostatic balance. So if hydrostatic balance is valid, remember the main assumption here is that the vertical motions are negligible. The air column was assumed to be stationary, and we will see that this is pretty much true, except for exceptional cases of very fast motions in convections, as we said. This also explains why when you go on top of a mountain, the pressure decreases, right? You can feel, of course, oxygen also decreases if you go high enough, because of all the profiles, the way they work from the surface to the top of the atmosphere. But essentially, the height of the air column above begins to become less and less as you go away from sea level pressure, right? Sea level pressure, you have 1013 pascals or millibars, but as you go up in the mountain, pressure drops off. There are other consequences of that. The water boils at a lower temperature, etc., right? So these are the kind of cute things that come directly out of the hydrostatic pressure. And when we say we have to be sure it works, the consequences you feel when you go away from the surface tells you that this is probably true, right? The airplane, for example, is pressurized because it's flying up in the upper troposphere, and so on, right? Oxygen also drops. Entire air mass drops. It becomes rarer. Density drops, pressure drops, temperature drops, and so on, right? This is why the hydrostatic balance is so important. This is why you need to make sure that you understood how we derived it and how simple the expression is. dP dz equals rho g. Very simple equation, but has lots of consequences. Make sure you understood it.